You should thank the moon. Your existence depends on it, not just your life, your entire species, every human who's ever lived, every civilization that's ever risen, every moment of happiness, every triumph, every breath you've taken, all of it owes its existence to a collision that happened 4.5 billion years ago. A collision so violent that it nearly destroyed the young Earth. Without that collision, without the moon, you wouldn't exist. But the moon is also slowly killing the planet. Right now, this very second, the moon is stealing Earth's rotation. It's pulling our planet like a cosmic anchor, dragging us, slowing us down. Days are getting longer, microseconds per century, but accumulating, inexorable, unstoppable. And in the deep future, not millions of years, not billions, but in the relatively near cosmic term, Earth's rotation will stop entirely. We'll become tidally locked to the moon. One side permanently facing our satellite, the other side in eternal darkness. And life, as we know it, will become impossible. The moon saved us from oblivion, but in saving us, it sentenced us to eventual sterility. And we're living in the narrow window between those two states. We're in the brief, miraculous period where the moon is close enough to stabilize our climate, but not so close that it's locked our rotation completely. We're in the sweet spot, and we have no idea how much time we have left before that window closes. Let me show you what the moon actually saved us from. 4.6 billion years ago, the solar system was chaos. Planets were still forming, asteroids were colliding, gravity was rearranging matter on incomprehensible scales, and in the inner solar system, a Mars-sized protoplanet we call Theia was orbiting the young sun, and it was on a collision course with Earth. Earth at that time was already a planet. It had a core, it had a solid crust, but it was smaller than today. It had no moon. It rotated much faster. A day was only about 6 hours long, and it was unstable, chaotic. The axis of rotation wobbled wildly, and then Theia hit. The collision wasn't a glancing blow, it was catastrophic. Theia slammed into Earth at an angle. The impact was so violent that it nearly destroyed both worlds. Theia was obliterated. Its core merged with Earth's core, its mantle was vaporized, and the debris, the shattered remains of Theia, combined with material torn from Earth's crust, was ejected into orbit. That debris coalesced. It formed a ring around Earth, and within a few decades, that ring consolidated into a single body, the moon. The moon wasn't created from nothing, it was created from catastrophe. It's made of the remains of a dead world. It's a monument to near extinction. And from that catastrophe, life became possible because the moon stabilized everything. First, the collision itself slowed Earth's rotation. Before the impact, days were 6 hours. After the collision, they were about 18 hours, longer, more stable. And the moon in its orbit has continued to slow us down. But more importantly, the moon stabilized Earth's tilt. A planet's axial tilt, the angle at which it rotates relative to its orbital plane, determines climate. Earth's tilt is about 23.5 degrees. That tilt gives us seasons. It distributes solar energy across latitudes. It prevents the poles from getting too cold and the equator from getting too hot. It creates a relatively stable climate. Without the moon, Earth's tilt would not be 23.5 degrees. It would be chaotic. It would wobble between extremes, sometimes tilted at 80 degrees, sometimes at 40 degrees, sometimes nearly vertical. The tilt would change unpredictably over thousands of years, driven by gravitational perturbations from other planets. And as the tilt changed, the climate would become catastrophic. When tilted too far, the poles would receive intense sunlight. The ice would melt, sea levels would rise. When tilted nearly vertical, the poles would be in darkness. Ice sheets would advance. Glaciers would cover the continents. The climate would be in constant chaos. Violent shifts between extremes, no stability, no predictability. And in that chaos, complex life, especially intelligent life, could not evolve. Civilizations could not rise. We could not exist. But the moon stabilizes the tilt. The moon's gravity acts as a gyroscope. It locks Earth's axis in place. The tilt remains nearly constant at 23.5 degrees. The climate remains relatively stable. And in that stability, life evolved. In that stability, intelligence emerged. In that stability, we came to exist. Without the moon, we are not here. Life might exist on Earth. Simple life, microbes, but nothing complex, nothing conscious, nothing that looks at the stars and wonders. We owe everything to the moon. But here the narrative becomes darkly ironic. The moon is slowly moving away from Earth. The moon orbits Earth at a distance of about 384,000 kilometers, but it is not a fixed distance. The moon is gradually receding. Every year it moves about 3.8 centimeters farther away. It has been doing this for billions of years and will continue forever. As the moon recedes, its gravitational influence weakens. As its gravitational influence weakens, it will become less effective at stabilizing Earth's tilt. Eventually, the moon will be so far away that it will not be able to stabilize our planet's axis anymore, and Earth's tilt will begin to wobble again. But that is a far future problem. The immediate problem is that while the moon is receding, it is doing something else. It is slowing us down. This happens through tidal friction. The moon's gravity pulls on Earth. It creates bulges in our oceans and in our crust itself. This solid Earth. The rock beneath your feet actually deforms. It rises and falls as the moon orbits overhead. The ocean tides rise and fall. And as the Earth rotates, as the planet spins faster than the moon orbits, there is friction. The tidal bulges are dragged ahead of the moon by Earth's rotation. That dragging creates friction. The friction dissipates energy, and that energy is converted into heat. The friction also exerts a torque on Earth, a twisting force that opposes the planet's rotation. And that torque is slowing us down. Every day that passes, Earth rotates slightly slower than the day before. It's microscopically small, about 1.7 milliseconds per century, but it's inexorable. And it's been happening for billions of years. When Earth first formed, when the moon first coalesced from Theia's remains, a day was about 18 hours. Now, it's 24 hours. In the distant future, if the moon stays in orbit long enough, a day could be 30 hours, or 40, or 50. And eventually, if the moon stays in orbit long enough, a day will become as long as a month. Earth will become tidally locked to the moon. One rotation will take the same time as one orbit. The moon will hang in the sky, always in the same position, never rising, never setting. And the same side of Earth will always face the moon. Let me make this physical. Let me show you what that actually means. Imagine standing on Earth in the distant future. So far in the future that billions of years have passed. The moon hangs in the sky above you, always in the same place, not moving, not rising, not setting, just there, fixed. And the side of Earth facing the moon is bathed in constant light, not daylight, but moonlight. Faint, but unending. And on the other side of the planet, the side facing away from the moon, there's perpetual darkness. The sun rises and sets normally for those regions, but the moon is below the horizon. They never see it. It's a world split into day and night that never rotate. A world where the climate on the near side becomes baked by constant moonlight reflected from a stable, never-setting moon. And the far side becomes frozen, locked in darkness and cold. And life as we know it can't survive in that configuration. But here's what's genuinely terrifying. We don't know how long we have. The rate of tidal deceleration isn't constant. It depends on several factors: the shape of Earth, the viscosity of Earth's interior, the amount of tidal friction in the oceans, the resonance between Earth's rotation and the Moon's orbit. And some of those factors change over geological time. So we can't calculate exactly when tidal locking will occur. We can make estimates. Some models suggest it would take about 50 billion years. Other models suggest it could happen in 20 billion years. And there are variables we don't fully understand that could dramatically accelerate or decelerate the process, which means we're uncertain. We know it's coming, we know it's inevitable, but we don't know when. And that uncertainty is worse than knowing, because we can't prepare, we can't plan. We can only know that at some point in the deep future, Earth's rotation will slow to the point where the planet becomes tidally locked to the Moon. And when that happens, the habitable zone for life will shrink dramatically. But let me show you something even more disturbing. We're not waiting for tidal locking to become a problem. The tidal deceleration is already affecting us. The Moon is already slowing us down, and that deceleration has consequences. First, tidal energy is being dissipated as heat rather than maintaining Earth's rotation. That internal heat is warming Earth's interior by a few terawatts globally. This internal heat interacts with our climate in ways we do not fully understand. Second, tidal friction in the oceans is dissipating energy that could drive ocean currents. The Moon's gravity creates tides that move water and generate currents. Those currents transport heat and help regulate climate. As tidal friction increases, tidal currents become weaker because energy is dissipated first. Weaker tidal currents mean less heat transport and less ocean mixing. Reduced circulation affects global climate patterns. Third, tidal forces themselves are increasing in the future due to orbital dynamics reversing. The Moon is moving away now. But billions of years from now, it could move back toward Earth. As the Moon moves closer, tidal forces will intensify and tidal friction will accelerate. The deceleration of Earth's rotation will speed up, due to increased tidal friction. Instead of slowing by milliseconds per century, Earth could slow by entire seconds per millennium. Days could lengthen by hours per 1,000 years and shift from 24 hours to 30 or 40 hours over a few million years. At that point, the climate would begin to destabilize with massive tidal bulges and extreme ocean tides. Coastal regions would be devastated by tidal surges and flooding. The atmosphere would develop new circulation patterns that we cannot predict. Life would begin to suffer as environmental rhythms change. We do not know if life can adapt to such dramatic changes in day length and tides. Earth's biosphere evolved with a 24-hour day, and circadian rhythms are deeply embedded. If days become 30, 40, or 50 hours, organisms would need to readjust their internal clocks. Evolution would need time and selection pressure to rewire species, and that takes generations. If day length changes fast enough, the biosphere might not adapt and species could go extinct. Entire ecosystems and human civilization built around 24-hour cycles could collapse. We would struggle to grow crops, maintain sleep cycles, and survive in a destabilized climate. In all likelihood, we would fail to maintain civilization as we know it. But before that happens, there's another problem. The Moon is also affecting Earth's magnetic field. Earth's magnetic field is generated by the motion of molten iron in the outer core. That molten iron is in motion because the core is rotating and cooling, and the cooling is driven in part by the heat dissipated by tidal friction. More tidal friction means more heat. More heat means more thermal convection in the core. More convection means stronger magnetic field generation. So as tidal friction has increased over Earth's history, the magnetic field has generally gotten stronger. But the relationship is complex, and as tidal friction continues to increase, as days continue to lengthen, the dynamics of the core might change. The pattern of convection might shift, and the magnetic field might weaken. And if the magnetic field weakens, Earth loses protection from solar radiation. The solar wind would penetrate deeper into the atmosphere. More radiation would reach the surface, and the climate would become harsher. Life would suffer again. But let me show you the real horror. The problem isn't that the moon is slowing us down. The problem is that we're living in a specific window of time where the moon's effects are balanced. The moon is far enough away that it's not locking our rotation, but close enough that it's stabilizing our tilt. Days are long enough to develop complex life, but not so long that civilization is impossible. We're in the Goldilocks zone. Not too much tidal locking, not too little. Not too short days, not too long. And that window is closing. In the past, Earth had shorter days and a closer moon. The moon was near enough to stabilize the tilt, but not so near that we were experiencing extreme tidal forces. But as the moon has receded, as days have lengthened, we've been moving through the habitable window. We're currently in the middle of that window, the optimal zone for complex life, for civilization. But we're passing through it.